All right, in this exercise, let's review that activity we did on Friday, or the review for the test. All right, let's just start off, launch into it. What is the number 111000001 in decimal? How do I convert that? Well, I write down my place values if I forgot what they are, and those are powers of 2. So I have a 1s, 2s, 4s, 8, 16, 32, 64, 128th place. So I just add up my place values, and I get the number 225 in decimal. So this is a 128 plus a 64 plus a 32 plus 1. Add those up, I get 225 decimal. All right. What is the largest value I can fit into 4 bits? Just write down 4 ones and add it up. So 4 ones, 1111, that's 8 plus 4 plus 2 plus 1. Just add up the place values. There you go. And you get 15. I'll explain there's a mathematical way to generalize this later, and I'll explain that in the next slide. All right. What is the largest value I can fit in 8 bits? Well, write down 8 ones, add up the place values, 255. 255 is the biggest number you can fit into 8 ones and zeros. Here's the generalization for this in binary. The largest number you can fit in n bits is 2 to the n minus 1. So if we have 4 bits, that number is 2 to the 4th minus 1, which is 2 to the 4th is 16, minus 1 is 15. The biggest number we can store in 4 bits is 15. Now, because we start counting at 0, we have 2 to the n possible symbols. So if in 4 bits, I have 2 to the 4th possible values because I start at 0. Just like with 3 digits, 3 decimal digits, the biggest one is 999, but that's 1,000 possible values if I start counting at 0. So if the biggest number you can store in any given number of bits is 2 to the n minus 1. That's an important formula to memorize. So again, applying that to 8 bits. Oh, no, sorry, 3 bits. If we have 3 bits, what's the biggest number we can store in 3 bits? 2 to the n minus 1, that's 7. How many possible combinations is that? How many possible values can I store in 3 bits? 8 values because I start at 0. What about 4 bits? 2 to the 4th. The biggest number I can store in 4 bits is 2 to the 4th minus 1, which is 15. And that is 16 possible values because I start counting at 0. So 2 to the n minus 1, important formula to remember. Just what's the largest number you can store in a given number of bits? 2 to the n minus 1, where n is the number of bits. All right. Here's a 4-bit binary number. What happens if I add 1 to this? Well, the number is going to be, well, you can tell this is, what's the biggest number here? This is going to be 15, or what is this? It's 15. If I add them up, 15. I also know I have 4 bits. What's the biggest number I can store in 4 bits? 2 to the 4th minus 1. What is that? 15. If I add 1 to this, I have 16. That is too big to store in 4 bits. The number will get bigger, will be a bigger number than I can represent using the storage space that I have. So this is called an overflow. The result was too large to store in a given number of bits. So imagine, like on your test, here's a test taking tip. You have a math problem and the answer is incorrect. You added 2 numbers and the result was too large, or maybe you subtracted 2 numbers and the result wasn't right either. Ask yourself, like, do the math problem and ask yourself if the result can be represented with the number of bits you have. So if you have to add 2 numbers, if the problem says you add these 2 numbers together and they're 4-bit numbers and the result is wrong, well, is the result something you can store in 4 bits? If you're asked, you're told you add 2 numbers together and the result is wrong. Well, if it's an 8-bit number and the result is greater than 255, well, then the result was too big to store and you got one of these overflow errors. So check to see if the result is something that is too large for the number of bits that you've been allocated. And that way to figure out the number of bits, or that largest possible value, that is the 2 to the n minus 1 formula. All right, what about this? can I store this number in 4 bits? Well, obviously not, right? Because this number is bigger than 4 bits. What happens to these 4 bits on the right here? Sorry, there we go. What happens to them? Well, there's no room for them. There's no bits to store these values in. So they just get thrown away. This number effectively just gets, the right part just gets chopped off. We lose precision and this number gets rounded down. So this is a rounding error. We have a number that has more precision than we can actually store in a given number of bits. So you can obviously see this number is too big to store in 4 bits. What happens to those extra bits? They get discarded, and the net result is that that number is rounded down. All right. Here's an interesting factoid about the way computers store numbers internally. There are certain numbers that cannot be represented using the floating point format that CPUs actually use, and it can produce some strange results. You could try this. I'm not making this up. Open up an online Python interpreter and print out what the result of 0.6 plus 0.7 is. You'll find that it is 1.299, a whole bunch of 9s followed by an 8. This is incorrect. It's 1.3, but we can't represent 1.3 can't be represented using the format that CPUs or computers actually use to represent numbers. Now, you might be wondering, why does it work on your calculator? It's because your calculator is using a different system or a different format for storing the numbers. But takeaway there is it's crazy. Some numbers cannot actually be represented. All right, here's what is the bigger number here? So A in hex or this number in binary? Well, in hex, the numbers are the same with decimal up to 9. And then we start counting with letters. So 0 0, 1 is 1, 2 is 2, 9 is 9, 10 is a hex A, 11 is a hex B, 12 is a hex C, 13 is a D, 14 is an E, and 15 is an F. So A is a 10, right? So what's bigger, 10 or 17? Well, in this case, the 17 is obviously bigger. I actually meant to put this on the worksheet. But you can do, it's the same thing. A is a 10 in hex. What's 1001 in binary? It's a 9. So in this case, the A is bigger. 10 is bigger than a 9. So just convert them to the same number base. All right. ASCII character. What ASCII character is? This number right here. Let's make it bold. I don't know. Let's make it bold. Sure. All right. So now the hex table that we gave you in this problem is contrived. It doesn't have binary and it doesn't have decimal. It just has hex. So how do we convert this number to hex? Well, split the value in half, and we're going to assign a hex symbol to each half. Well, what is this number on my dog is destroying things. What number is this on the left? It's a 4. There's a 1 in the 4's place. 1's place, 2's place, 4 place. 1, 2, 4. That's a 1 in the 4's place. So that is a hex 4. What about this thing on the right? That is a 1. That's a hex 1. So it's a hex 41. If you look up 41 in the table, you will see that is a capital A. All right. Now let's move on to the last one. What is the number? What is the character that corresponds to 90 decimal? Well, just convert 90 to binary. And if you don't remember how to do that, use the subtraction method. How many 64s can I get out of this number? How many 32s can I get out of this number? How many 16s? And so convert this number to binary and then split it in half. And we're going to assign a hex digit to each side. Well, what is this number on the left? That's a 5, which is a hex 5. What about this number on the right? That is a hex A. And I remember that because we count 9 and 9. Hex is the same up to 9. And then at 10, a 10 becomes a hexadecimal A. And I remember that because I can see 2 10s in this number. There's 10, 10 is an A. So this is the hexadecimal number 5A. And then I just look up 5A in the ASCII table, and I see that that is a capital Z. So that is how to solve these problems there. I hope you found this helpful. I think if you understand this, you will do well on certainly on the portions of the test that cover this material.